Thank you very much. And hello and welcome. We are going to talk about cloud native supply chains, how they can be attacked and consequently defended. I'm very thankful to my colleague Francesco for co-authoring this talk with me. So we'll take a risk-based view of supply chain attacks against our systems. We'll compare different controls that are available to us in this modern day and age. We will examine how they all hang together and propose a solution for end-to-end supply chain security. I am, as my gracious hosts introduced me, Andy, CEO and founder at Control Plane. I also do pro bono and community work in tag security, where we help to assure software that is coming through the CNCF. So as a project like Flux or Prometheus or not Kubernetes itself, we didn't exist then, but as they graduate through the different stages of CNCF maturity, we provide a community-driven assurance. It's fantastically interesting, if I don't say so myself, and it's a place that I learned a huge amount about not only cloud-native security from a generalized maintainer perspective, but also about how to be successful in open source and a lot of the collaborative points. So I very strongly encourage you to join if you are interested. We have an EMEA time zoned meeting every second Wednesday at 1 p.m. London time. That's all on the repo, Tag Security CNCF. Please join us if you are so inclined. And finally, I work at Open UK with my esteemed friend, Mr. Matt Jarvis, as well, where we look to try and assist regulation for open data, open source, and open hardware. And again, it's a fantastic community of voluntary professionals. I strongly encourage you just to observe any of those things if you find them interesting. Okay, I've also written more than I speak, unbelievably. This book with my dear friend, Mr. Michael Hasselblass, is available as a free 50% download behind an email wall. The link is there as well. And various different attacks on Kubernetes, all good stuff to throw at Madhu's Kube Goat as well, if we're following on from the last fantastic presentation. Okay, we are Control Plane, spread across the world, and this is our agenda. What is the problem? How do we threat model it, and how shall we fix it? Okay, what are these existential questions we ask ourselves? This is only really addressing the tip of the iceberg, and there is plenty more, but that is a TLDR. What is the problem? So what is this nebulous concept of a supply chain? It is anything that we depend upon across any sector or vertical. In a military scenario, this is, of course, hardware and software that run on vehicles, weapons even, and understanding from where did this thing come, who built it, and do we really trust it? There's potential for other nation states to interfere in each other's supply chains, of course. Pharmaceutically, this is what is the composition of the chemical compound that I'm going to feed to a human. We have such strict assurance and scrutiny on those things. We must ensure that we feed people the correct dosage, the correct compound. For software, what does this mean then? It is anything that constitutes the final application running in production. That definition is unwieldy and monstrous, but that's what we're left with. This is how open source is advantageous for everybody by giving very low barrier to entry and massive amounts of code reuse, but it also comes with built-in anonymity and trust that is being challenged. Now nation states have got wind of it, and now every organization is basically an open source organization. So this is a super simplified supply chain. The problem here is if our nefarious adversary, the dread pirate Captain Hashjack, can get his mucky paws on one of our dependencies, ultimately he is then able to run code in production. This is the nightmare scenario that we look to avoid. The way he does that in this case is by infecting a third-party dependency. That could be an operating system, probably not that likely. An application dependency, well, open source with everything in NPM and the PyPI registry and Ruby gems, there's a huge amount of code there, millions and millions of lines of code, and it is not as well scrutinized as it should be. That story has got dramatically better over the past 2 years, thanks to things like SolarWinds. we can now perform a more in-depth analysis with machine learning approaches as well, which can help to indicate whether code is malicious, irrespective of whether there's an existing signature for that type of attack. But of course, mileage will vary. There is not generalized AI yet, so it still makes sense to defend ourselves against the inevitable. Or finally, it could be a piece of vendor software. Vendor software really is the worst form of attack, the worst vector in this situation. SolarWinds distributed signed, legitimate, but compromised software to its consumers. As a producer, the expectation is that that producer is not only signing so that we have that signature and that trust, and we can cryptographically verify via a side channel that this is the artifact that they gave to us, but also tightened security practices, a low mean time to remediation for compromises or for upstream issues with their supply chain. And in this case, a foreign nation state adversary was able to get into their build infrastructure, subvert a build, and push malicious software into their signing infrastructure, which was then legitimately rubber stamped and passed on to their consumers. So as we see, the operating system is a bit difficult. The application dependency landscape is massive and the current form of battleground. And the vendor landscape is far more insidious because we have an existing deep level of trust with any vendor that we exchange financial information with. Ultimately, if we're paying for a service, then we have contracts and legals in place that give us a higher level of trust and expectation. It's not always justified. Okay, so what do we do with one of these implants? Once we've got code into the supply chain for an organization we're attacking, then we want to get remote command and control of something in their infrastructure. There are various off-the-shelf products to do this. There are some leaked nation-state products to do this. There are some private hacking team products, or you could just use Bash, which of course is my Stockholm syndrome. Ultimately, all of these things enable command and control. So we place an implant onto the victim's machine that executes on their machine and fires some sort of communication back to an endpoint that the attacker controls. In this case, we're doing a reverse TCP shell. Again, we can just do this with Bash. There are other ways to do it. We can use third parties. IRC used to be a popular mechanism. This is very similar to what botnets do. Maintaining command and control, or C2. I mean, we can even use strange stateless things like ICMP to gradually compress and leak data. We can push through third-party repositories, anything that allows mutability. GitHub, container registries, gives us a potential command and control channel. There's a big lesson here, which is we're supposed to be behind the firewall, but actually the way this works busts through firewalls unless we specifically enable egress filtering, which is, as the Log4Shell vulnerability showed to us, very rare indeed. So let's just have a look at why egress filtering is mandatory for any seriously secure organization, or securely serious. The dread pirate Captain Hashjack is sneaking his code into this third-party dependency. What happens next? Well, that malicious dependency gets bundled up into developers' code. This might be through typo squatting, where left pad with a hyphen is duplicated by left pad without a hyphen, just one word. Developer adds that to their package JSON. They make a typo, but the same code is duplicated to both endpoints. The attacker controls one of them, and the other is the legitimate version. The attacker can then continue to duplicate legitimate code to their typo squatted package until they want to enable an attack. Maybe they've got 100,000 downloads. At that point, they inject malicious code. If dependencies aren't pinned, it will just be installed by the next version. And then there is a window of risk during which malicious code will be uploaded and run in CI, and then potentially, as we can see here, if it's in the dependency, in the developer code, and then into the malicious container image, it will then be built into that container that's deployed into production. So we have a front-end deployment here with an implant in. This implant is a command and control instigator of some description, and that makes this reverse shell call to an attacker-controlled endpoint. The important thing to note here is there are plenty of ways to stop this from happening. Intrusion detection is the last line of defense for anything, of course. We can also, as I've been talking about, prevent outbound egress to unknown IPs. Now, most of the time, because egress filtering has an overhead for humans to manage, and a developer overhead as well, because we don't necessarily expect an outbound connection to just suddenly fail in production versus a different environment, for example. However, in the event of somebody gaining remote code execution in your production infrastructure, which is exactly what happened with Log4Shell, widely deployed code, but nevertheless, nothing is inherently secure, and we can't guarantee that there are no remote code execution vulnerabilities in our code in production today. So we defend in depth, and we will get more into that as we progress through the talk. And so at this point, once the attacker has established some presence, they can run with the permissions of the workload in the cluster, and they can begin to escalate, to observe the visible horizon, and to look how to pivot into other endpoints on the system as well. So how do we attack a supply chain? We can start with a supplier. This is someone who is providing code into the system. So we're talking again about our package repositories, about our operating systems. We can infect a trusted package that runs as root. I hope we're not doubly getting releases straight from GitHub, but we probably are in some places. Docker normalized that to a large extent. Not that it wasn't there already. We can infect the source code. If someone leaves their laptop open in a coffee shop, it's not very much effort to just drop an implant on there and then again gain remote control on that. And then use the developer's privilege, their Git keys, the SSH, 2FA, sorry, not 2FA, a GPG signature. 2FA if they're going to steal session tokens for OAuth 2, for example, which could then directly impact production. The source repository, again, it kind of depends on where that repository is hosted. Self-hosted is a bit easier to attack potentially than attacking GitHub infrastructure, which is very unlikely. So instead, attacking perhaps GitHub authentication, stealing credentials might be a more likely route there. Build infrastructure is the SolarWinds question, and the runtime environment is, can we infect the base image almost for containers today? Okay, so let's take a quick look at what's possible in terms of supply chain threats. It is pretty bad. If there's anything that computer security teaches us, is it can always get worse. What we don't really want to see, of course, is further supply chain attacks. And this concept of a stream of attacks is really where the amplification of a supply chain attack can be so harrowing. And again, SolarWinds is the poster child in many ways. The attackers had so many targets to choose from that there wasn't evidence of any attack in the majority. But then they attacked Microsoft a lot, that they attacked the UK government infrastructure, sorry, US government infrastructure, as well as a number of private companies of sort of less repute. But the extent of the attack was huge. So all of these things are problematic, but amplifying and sort of escalating the attack across a wide network is really the terrifying situation. Tag security, maintain a list of supply chain compromises. Kudos to everybody who contributes into this as well. If you'd like to see what broadly we're having problems with in this day and age, here is a short list. Okay, so that was a quick run through. Let's have a look at the problem space. Why is this so difficult? Because of the expanse, because of the number of pieces of software, the amount of contributors, and ultimately also the speed of updates. A lot of software installed is not at the latest version, and CVEs are released. It is only really with the dawn of containers that we have started software composition analysis en masse. Obviously, we then have a secondary problem, which is that CVEs don't necessarily correlate correctly, and signing off whether to use a potentially vulnerable piece of software in production is the hardest job in security. Vulnerability assessors take a personal risk, gamble, if you like, in doing so. There are mechanisms, including VEX, to attempt to simplify this process, but it all hinges on trust. And ultimately, we'll dig into trust slightly more. Ultimately, this problem space is huge because traditionally we've trusted everybody, and now we've realized there are more nefarious actors involved, and we need to reassess exactly who and why we trust what and who. What a sentence. Okay, so what will we do about this problem? We can just ignore everything. Well, that won't work. Financial institutions, governments, critical national infrastructure, everybody is using open source software. It has eaten the world in the way that software was predicted to, and we're infinitely grateful. I'm tremendously pleased at the fact. We use them and don't care. Well, we wouldn't do that. That's not accepting risk. That is a blasé, laissez-faire attitude and professional negligence. Or we secure everything. Well, we can never secure anything. Nothing is entirely secure. And this is a recipe for disaster because we will not have usable security. We will not have developer retention. And we'll probably have a frustrated egging of the security department at the appropriate juncture. So instead, we undertake threat models. Then we map them to standards and best practices, we build out reference architectures, and we incrementally improve. This is how I undertake my consulting engagements. This is how we work best with large organizational transformations, large departments, etc. For small teams, you can even take a lot of this off the shelf. So hooray for open source. All right, so let's have a look at a threat model. Threat modeling supply chains. We will look at a system a little bit like this. This high-level reference architecture as an example. So what do we have here? Well, first of all, we have artifacts. And that artifact storage at the top is some form of registry. So that may include binaries, images, it might be a nexus, it might be an artifactory, it might be just containers if we've decided to put everything in an OCI compatible architect. Beneath that, we have a metadata store. Metadata is anything generated in the build process. So test and vulnerability reports, pipeline executions, SBOMs, VEX documents, manual interventions, etc. It's critical that that is signed, and we'll look at how the signing interplays with this in a moment. Then the build might have a local runtime temporary storage for artifacts being pushed to the main artifact repository. This seems normal. Having a cache is not unusual, but it's another point for tampering and something we should be cognizant of. And then finally, we have an attestation phase here with node attesters, workload attesters, and pipeline observers, which capture verifiable metadata from pipeline processes. These can also be used to feed an admission controller at runtime, both when the pipeline is instantiated, but also when the artifact is finally deployed to production. Okay, so that's what we'll look at. What will we do? Well, systematically, threat modeling is about unifying different ideas and approaches to a complex problem space. Systems are inherently complex in the technological landscape that we inhabit. This gives us an opportunity to take dissenting or conflicting views, find the middle ground, draw the security architecture or the topography of the system on a whiteboard and make sure that we all agree. Because often there is not agreement around these things. Once we have that idea, we look at how data flows through the system. What is the classification of data at each specific point? Are there some obvious anomalies where we wouldn't want data crossing from one place to another? How do we then extract security controls from those risks that we find? And then how do we build out attack trees which show us paths that the attacker could take through the system that we then apply countermeasures and controls to in order to quantify and measurably secure the system in a way that makes sense today and also lives in perpetuity for future maintainers of the system who otherwise may not have a clear idea of why a particular control exists. Okay, so we ask, first of all, what are we building? This is diagrams, project background, all sorts of stakeholders, our initial architecture diagrams. What's the worst that could happen? Catastrophization incarnate. No wrong answers, going wild, quantum cryptography breaks the internet, for example. Okay, then we go to stage 3. How can we reduce the risk of bad things happening? Well, we probably can't invest in quantum cryptography research to stay ahead of things. We know that there are quantum resistant algorithms coming out or being tested at internet scale by Google and Cloudflare and the like. So we should probably make sure we just have a cipher review. If we really need TLS 1.2 support, we can leave it on. But if we don't, maybe it's beneficial to enable it. To disable TLS 1.2. But then we put that in a list of other threats, like there's currently no authentication on the main site. Okay, well, the threat there is that somebody comes and steals all the data. That is the highest order and the highest precedence to fix. And TLS 1.2, 1.3 bike shedding can kind of wait until we've actually made sensible security decisions for the system. So all of these things are quantified, ordered, and give us a view into actually securing a system instead of kind of hand-waving the, it's not necessarily FUD, but we want to make decisions as clear as possible to get buy-in from the operators and developers to actually perform some of the work and make sure that we have tests that validate those things. And then stage 4 is just rerunning the loop. Did we do a good job? If not, let's capture those as risks for the next time through this process. If we did, happy days. Let's schedule the next time we do this, either the next major release, 6, 12, 18 months, whatever the system needs. Okay, so what are we building? Well, we're looking at the supply chain components and data flows of our CI. We want to understand what the supply chain is for. The confidentiality, integrity, and availability of the system are the business impacts. If the system suddenly is entirely public and everyone can read all the data, are we safe? Probably not. Integrity, if people start tampering with artifacts, injecting implants, are we safe? Well, we might be, probably not, but our consumers certainly will not be. And availability, will we have a business impact if we can't run the system? Yes, we won't be able to package and sell our software. And then the operating model, looking at how teams actually use the thing internally. A quick shout out to my esteemed colleague, Mr. Nick Simpson from the control plane security team. These are some toxic combinations. These would typically be individual threat models because one major focus on threat modeling is to scope things down as narrowly and tightly as possible to avoid, again, bike shedding, generalized brain overload and scope creep. So it makes a lot of sense to capture everything, but descoping and putting into a pile for the next threat model or for one layer of abstraction further out on a threat model is a helpful process because it means we can complete a threat model in a reasonable amount of days instead of just an unending process. So what's the worst that could happen? We play through some scenarios. The business may have an awareness of these. We can also transmute scenarios from other organizations. We can use the SolarWinds example, for example. And then we look at threats. We gather these threats from internal threat libraries, external MITRE, financial services attack vectors from the CNCF, OSINT, other SIGs and the tags. We look at the attack path. These are the steps required to perform a compromise. Sometimes there are junctures where multiple compromises can occur from one level, from one point of entry. And then we build attack trees to make sure everybody agrees. There's nothing worse than an abstract, hand-wavy security talk, he says, self-referentially, or conversation, because a lack of understanding means that if it's not clearly communicated, not everybody can contribute. And really, the magic of security is not in security experts, it's in understanding what everybody else thinks and then helping to prioritize those threats. So it's not about coming in and just sort of waving your arms about post-quantum cryptography, as I did. It's more about understanding from the developers, where do you think the threats to this system are? You work with it every day. You're intimately aware of design decisions and how things have changed over time. So the attack trees are a way of going back to those people and saying, this is what we think an attacker will do to get into the system. Do you agree? And they can say, well, actually, no, because that jump you've made there, there's no routing between those two systems. So you can't actually do a TCP-based jump across that network. And then we can say, oh, fine, we didn't understand that from the initial diagrams. Let's go and make sure they're up to date and correct. What about this route? Oh, yeah, that's a problem. Again, bringing everyone forward together is far more outcome focused than just kind of hypothesizing on these things in isolation. Lots of threats. I mentioned these briefly. We're looking to define those and then play those back over what we suspect is the problem. So, threats to supply chain security properties. Now, we really must preserve the source, build, and runtime integrity along our supply chain. We'll look in detail at how exactly these work and start off with how integrity can be compromised. So these threats can be quite useful, but the exploitation is obviously a lot more useful. Let's start at the top of the diagram and work down. So in the replace artifacts in the top right, if the artifact is built, tested, signed, and pushed to an artifact storage, and we can then upload our own signature and our own artifact, we would have had to compromise the signing key to do that, of course. Then it doesn't matter what happened in the rest of the build chain because we've just injected our implant straight in there. Obviously, that's a bad day. We can bypass CI/CD entirely, as in if we can get deployment to production. Again, we may need to falsify some signatures, but if we can just deploy to production because we've got into the cluster, then we can just run directly in production. Of course, from a Kubernetes perspective, if we go through admission control, then we will be subject to signature tests potentially. If we go directly through, for example, shadow pods, we're not subject to admission control. That requires a kubelet compromise beforehand. Interestingly, Cryo are doing some work to perform validation on the runtime itself, which interestingly would help there. Then we'd require some reconfiguration of Cryo to run the thing, or just stop running in containers if we've compromised production. Bypassing CI/CD is a case of just running exploits. Down to compromised source control. Of course, if we compromise source control, we do leave a history in terms of what we've committed, but everything is built legitimately. So as long as our test infrastructure doesn't detect this, we will be able to deploy to production with our implant. A bad code submit, same kind of idea. Instead of altering the code in the version control system itself, we assume the identity of a developer by compromising their local machine or compromising their password. Ultimately, if there's no 2FA, we can just log into GitHub and do a commit that way. Then we have code tampering, the same kind of energy as the compromised source control and the bad code submit, except it's in between the source stage and the build stage. We'll map this onto an open framework in a few slides and just see how to remediate this kind of thing. And then finally, compromised build, platform, or process. So it accepts some commands from the orchestrator, but it runs whatever it wants, or there's a compromised CI/CD test runner. So once we've got those potential threats, we've identified them, we want to build attack trees. This is a visual representation of an attack on a system. These should enhance the threat modeling process. They can get complex. And again, scoping down really helps. Perception, ease of communication to stakeholders, and ultimately the ease of maintenance as the system inevitably lives for decades, maybe. Okay. How do we reduce the risk? Well, we look to conform to compliance requirements somewhere when we've identified them. My headphones decided to spontaneously run out of battery. I do apologize. Right. Yes, so controls the system under maintenance or under modeling should be aware of the compliance requirements it needs, and we can help to map those back onto the controls that we deploy. And we use these controls to break the attack train, train or chain. So essentially what we're doing here is there are branches to this attack tree, and we're looking to apply controls that slice through one or more of those branches. The decision we make when applying a control is it maintainable? Does it solve the problem that we're looking to solve? And does it have the side effect or the intended effect of cutting other branches at the same time in order to maximize the usability and the maintainability of the system? So we design for what we have now. In the future, if the system is under continued maintenance or it ships new features, security teams will want to know, do any of the existing controls help to mitigate attacks on the new features? Maybe they will, maybe they won't, and it makes sense to wind something back to implement new controls. These are the kind of things that an attack tree makes blindingly obvious, which is a British expression for which makes obvious. And so, did we do a good job? Just to highlight the importance of testing the controls implementation, it's all very well shipping these things, but they must be tested and done in an automated fashion. This then requires, of course, further advanced DevSecOps principles, securing extra test infrastructure. Ultimately, we're trying to reduce human interaction in the whole process. That comes with its own risk, of course, but is well within scope for more enlightened sets of maintainers. Okie dokie. So we understand that with threat modeling, we have a way to identify threats, somewhere to list them, and to assess how much damage can they make. We can prioritize, we can build controls to break attack trains, or they're going to be attack trains from now on, attack chains, or at the very least, slow down our adversary, the Dread Pirate Captain Hashjack, of course. Historically, not many people have focused on supply chains, but this has changed as software has eaten the world. So in the last few minutes, let's look at frameworks, some architectural recommendations, best practices, and controls to secure our supply chain. Okay, let's start from the SALSA provenance view. The recommendations from for provenance itself are sign things, distribute builds, and run policy as code. Provenance is something that says the producer created this thing, and as a consumer, I can prove that. So I'm proving that my producer created something. We'll dig more into that in a moment. The Cloud Native Security Whitepaper from Tag Security again suggests some defined dedicated steps here. Verifying, check that cryptographic verification of provenance, and metadata can do that for you. So signing a blob of JSON saying this hash has been scanned to have these things in it, created by these people, etc. SBOM, but also there's some other bits there that are more inherent in the fact the signature exists, which says at the time this was signed, the person in control of this signing key liked this thing enough to sign it. It does not mean it's correct. And that in itself is the huge seething pit of snakes in SBOM supply chain security. Why would we trust an SBOM if we're running software composition analysis on the software anyway? If it comes from a closed source vendor, yes, that makes some sense. If there's no introspection into the code, yeah, that still makes some sense there. But if somebody's attacked the upstream and we have a compromised package, the SBOM will also be compromised. So that cryptographic verification is only as good as the data we're verifying. There's a crap in, crap out aphorism in there. Onto automation, deterministic pipelines, absolutely essential. We have to have bit-for-bit binary reproducibility on the artifacts that we create. I build the same thing in two different places, I hash them both, and they should both match the hash. Temporal changes, time zones, locale ordering, this kind of thing, confound that and prevent actual hash comparison, but that's really essential for all of these things. Reproducibility is the keystone or the cornerstone upon which they are built or upon which the arch hangs. Controlled environments, of course, least privilege, we know this, and secure access stands to reason. We look at this in 5 different stages in the white paper. So just a run through quickly of the controls that we can apply to all of these stages. Verification, sign the commits. This is, I'll hide all the keys because they can be observed, but I carry a YubiKey around with me religiously, and that YubiKey contains a GPG signature, and that signature is used to say, when I made this Git commit to this GitHub or some repo or wherever it's going to be, I was in control of, I liked what I'm signing enough to sign it with the key I'm in control of. This is 2FA for identity. Everything here is based on identity. And yes, this does help to mitigate against, for example, locally compromised devices, because they still require that second, that 2FA signature, and it becomes more difficult. I mean, it's still possible to do because there is a cache involved and somebody could access the local machine, wait for you to commit, and then just jump straight in to use the GPG cache. But again, it makes things a lot more difficult and a lot more targeted. Automation, prevent committing secrets to repos. Fortunately, GitHub does a lot of this for us now. Coding conventions and scanning, yes, of course. Controlling environments, 4 eyes on pull requests. There is some contention about how exactly this is done. I really adore pair programming. In many places, that counts as 4 eyes, so we can commit into in something a bit more quickly, or a pair can merge their own commits. That does then reduce the kind of more general information disclosure across the group where people are looking at pull requests and reviewing. So salt to taste, your mileage will vary for your team. And protected branches, of course, we don't want people just pushing to production. Multi-factor authentication for everything, all our keys, everything should have MFA and 2FA. And short-lived ephemeral credentials. These are service and workload identities, machine identities, often anchored in trusted platform modules or trusted execution environments that mean hardware can sign information to prove that, again, it was in control of the key, and at that point, it liked it. That's incredibly useful to build up this huge chain of trust throughout an organization, and is very much the spiffy spire angle of choice. Of course, end user devices and keys should be secured properly. Third-party artifacts, we really care about verifying that they are the correct ones. Lots of tools will do that for you these days. Build based upon the source code, e.g. watch out for cache poisoning. Again, your mileage will vary here depending on the size of the caches you require. If you invalidate all caches all the time, your developers will not be very happy, and you'll probably suffer atrophy in those departments. Prioritize trusted package managers. Yes, of course. Google has released an assured open source package manager, which is awesome. Red Hat have, of course, been doing this for a long time. It sort of remains to be seen where that goes with recent announcements. Immutable SBOMs are useful. The trust question is really paramount here, and we should not trust an SBOM enough to avoid software composition analysis. And of course, scan software for vulnerabilities. There's all sorts, there's still a couple more here, just running through them quickly again. Validate runtime security of build workers. Make sure that you're actually running what you think you're running. We can anchor processes and TPMs here again. Testify Sec have got some really interesting products in the space. Automation, pipelines defined as code. Make sure they're transparent and not just a bunch of bash. Even if they are bash, make sure you're testing, got safe mode on. The BATS test system is excellent as well. Single use build workers. We can still inject cache into those, but polluting the build environment and risking ghosting of information between different builds is high risk. And segregating builds based upon data classification in the same way we do with production is sensible for an organization that has enough build workers to do that with. Segregating duties, yep, that's what I just duplicated myself in. Write output to a separate secured storage repo. So this is the concept of moving things through different repositories as they escalate towards production and ensuring there's segregation between them so that internal attackers, if you like, are not able to just jump straight in. And short-lived workload credentials, as always. Almost there. So verification here at the orchestration stage. Verify every step with those metadata posts. Use a store to manage that metadata. There are open source ones. Rotate and revoke, limit artifacts, and encrypt artifacts before distribution. Again, mileage will vary on this one. For some systems, this is a prerequisite. For a lot of open source systems, we can get away with not maintaining the IP because the contents are not private, they're open source, and just pushing the metadata. And then finally, verification here, admission control and production. We pull those artifacts and we push them somewhere that we trust and revalidate it. Okay, so a lot of that maps nicely to SALSA, the supply chain levels for software artifacts. The threat model of SALSA is similar and models many of the things that we've spoken about already in this presentation. This is a high level view with slightly less detail, but you can see there's plenty of opportunities for compromise at every stage. So SALSA has a view on how we secure things. It's useful in that it escalates from basics to level 4, which is fully comprehensive. We can see here it does so incrementally, which allows people to just adopt little pieces. We're looking at protecting the build. See, all we need to do for SALSA level 1 is script the build. Level 2, we want to use a service to actually run it. Level 3, we get a bit more difficult, isolation and ephemerality. But it's a useful way, as we can see, of identifying the potential risks and attacks that we have and defending against them. There is a concept of SALSA -1, which is saying it's all very well to talk about these advanced supply chain security features, but if you're running Jenkins on shared infrastructure, you're probably not in a great place to be thinking about instilling trust in your consumers. You probably want to make sure that you trust your own build system first, because otherwise we're back into this problem of trust. We sign something, we distribute it, and people say, lovely, we have an SBOM, that's got no vulnerabilities, let's deploy. We have to test the software composition of the artifacts that we take, and that is anchored on using a secure build system. So SALSA comes out of the Google Cloud mentality. Cloud build is SALSA compliant. That's a completely managed infrastructure with underlying physical security measures, etc. So just a note of strong consideration to ensure we secure the -1 in order to build upon a strong foundation. So lots of other good stuff here as we draw to a close. We want to harden our base image, distro-less containers with minimal dependencies, the Linux microcosm of containers. We use a standard security practices inside containers. We don't run as root, for example, and we make sure developers have the facility to debug images. Otherwise, again, we have to have developer compassion in the security tools and practices that we introduce. Then we get to the code. We sign our commits. Static analysis, reachability of potentially vulnerable functions, look at our dependencies, again, software and vulnerability composition, VEX for vulnerability exploitability exchange, which is the theoretical, can this vulnerability be exploited? Still not seeing widespread adoption. SBOM generation and OpenSSF CI scorecard, because we care about the infrastructure and the patterns and practices almost more than someone producing evidence. We have to be sure that the evidence is based on something useful. Then we can trace the build. Is there anomalous information, anomalous behavior? Is the build calling out to unknown IP addresses and endpoints? Then we get into pipeline metadata. This is all the good stuff about artifact registries and metadata there. The Untitled project is the foundation of a lot of this work. It uses bits of the updated framework as well. Spiffy Spire is secure production identity. Oh, hold on, the other one, secure production infrastructure for everybody. Secure production infrastructure for everybody. I always get that slightly wrong. The software factory, Frisker is for repeatable software artifacts. All of these things are the kind of leading edge of where we're getting to in builds. Some of them are still under development, and build migrations are huge. So incrementally adopting bits of these is useful as well. we can drop all our evidence into a lake or a ledger like Guac or Recor. And of course, signing everything is important. And then all of our scanning best practices in there. These are our runtime pieces. We should always have security contexts and hardened security modules, least privilege, RBAC, as Madhu mentioned previously, and drift analysis to make sure that what we deploy today is still secure tomorrow. So pipeline metadata can give us everything. I mean, I adore this. It's very useful. It's also a huge volume of data. And with that, we have completed our agenda. The problem space is massive. So threat modeling really helps in these cases.